Awesome. Yeah. So uh, the first thing I'll talk about is the abstract data type. So these are things that you might have heard from here and there. The abstract data type is the foundation on which you have the implementation of the data structures in various languages that you use. So for the same data structure, like abstract data type, which is lookup table, where you want to be able to look things up in time of one. In Java, you have hash table. In C++, you have unordered map. So you'll have different implementations and names in different places, but the concepts remain consistent across all of them. The abstract data type are just the idea of how you interface and interact with the data. The specific data structures in C++, which you should also be knowing for planning, are some of these that are listed over here. Unordered map and unordered set. They provide O of one access. Now you may think that the vector also provides you instant access. The difference why when you need an ordered map is when your data is not contiguous. So you do not know beforehand what index you need to query so that you can retrieve your data. When there is non-linear nature in the data and it's not contiguous, that's when you make the data itself the key of the data structure. And that's how the unordered map is used in practice. Map and set, they're both implemented using red-black trees, and it depends on the compiler that you're using. But they ensure that whenever you're adding or removing data, the data is sorted quickly so that you don't have to worry about that thing is happening efficiently under the hood. And it also ensures that there's no repetition. So the very idea of the abstract data type of a set in the set theory, there's no repetition. Priority queue. This is something that you would have encountered and hopefully you'll use in your homework one. The priority queue ensures that whatever you prioritize the most is at the beginning of the queue at any time you query. So anytime that you require the next best thing, you're able to retrieve it quickly. And the way this is implemented in C++ is using a min heap. A min heap is again an idea of a tree. Of a tree where each element above, if you're talking about of a min heap, is less than all of its children. And this keeps going on recursively. And because internally it's represented this way, whenever you remove an element, it automatically readjusts so that you're able to retrieve it. And this entire thing is happening very efficiently. Then there are the stack and queue. You have been using stack, and you'll require in the future for breadth first search and depth first search. So it's something that it's very common in planning, and you should be knowing. The breadth first search, you can think of it as a queue operation, where you have a queue that you're filling from the back, which is last in, and then you're removing the first element, first out. So each time you are expanding a node, you're looking at all of its neighbors, children, and then you are queuing them up at the back. And once you have completely expanded them, then you are getting rid of it. So the next element to expand is one of the children. This way you are doing coverage in a breadth first manner until you have covered all of them. The other way of doing this is depth first. We don't care about all the children, but we first want to get to the end as soon as possible. The depth first search is implemented as a stack, where you're looking at an element, you're putting it on top, looking at its children, putting that on top, and its children. So this keeps going until you reach the very end as far as you can. And then once it has no children, you keep going back, and then you look at the other siblings. And this way you keep going back until you have gone all the way to the start, and you have covered in sort of radially outward going direction everywhere. If you have implemented this depth first search as recursion, you might wonder, you didn't necessarily use the stack data structure. But under the hood, the compiler itself is using what's called the call stack. So all the function calls that you are calling within itself, you're calling like itself back, it is stacking them up and it is unloading them in the same fashion. So the abstract data type idea is held across wherever, however you're using it. Then you have the linked list, which is the singly linked list or doubly linked list. So what you should know is if you care about insertion, deletion, it's going to be faster with this pointer-based list. Then you have graph. This is something that will trouble you across the homeworks. In the first homework, what you had was an adjacency matrix, where it was very easy. You had grid, you were querying the neighbors using indexes. So using vectors, it's really easy. But in the future, you will have things like adjacency list and vertices, edges list. Adjacency list is kind of annoying. Vertices and edges are implemented as nodes. So each element data in your graph is a node which has attributes like cost, its neighbors, children, etc. And then you have multiple of these that you're keeping track of. And what this is allowing you is to maintain all the nonlinear connectivities between the data, between the different data, which is not possible in one single list that a vector constitutes. Then tree as well is another implemented as a struct which has children. It can be having two children, which is binary or more. I won't spend a lot of time on this because I want to go to the hands-on parts. The principles while choosing data structure, the one that matters the most is the frequency of operation. What operation do you think is going to be executed the most number of times? Because when your software scales, that operation will repeat so many times that a difference which is seemingly small now will amplify, and it will make a huge difference in that execution time of your software. If your most frequent operation is reading, the data is non-contiguous and you want to read the data and retrieve the value, you'd want to use something which has an O of 1 axis, which is like a hash table, a lookup table. If the most frequent thing you do is insertion deletion of elements which are in between, and you want to keep the connectivity, you'd use something which is a pointer-based list, where you can go to one of the elements, you can remove it, you can just patch up the pointers, and your list is still maintained. These are the operations that you need to be worried about, and also the data relationship. If your data is contiguous or incontiguous, that will determine if you're using a graph or you can get away with a vector. And also memory efficiency. If instead of a very hi-fi computer, you're implementing it on an embedded device, an Arduino, you have to worry not only about the time efficiency, but also if your device has enough memory to load those data structures. So you might have to do a trade-off where your data structure is not fast enough, but it is it's fitting inside the memory limits that you have so that you can get everything running together. Now we shall go on to some hands-on for debugging. Before we go to the hands-on, I'd like to give you a bit of a sense of what debugging is. Debugging is solving any error that your program runs into. It could be a bug which does not allow your program to compile at all. You have to debug what the like syntax error or typo is. It could be a runtime error where your program compiles, but at the time of execution, something goes wrong. It's a spec fault, something goes awfully wrong. Or it could be a logical error where a program compiles and runs till the end, but the output is completely different from what the correct output is. These are different kinds of errors that you may run into. And in all of this, you need to have some of your own principles on how you go about debugging this quickly so that you can figure out where the problem is and not get stuck on that for a very long time. For this recitation, I listed down some of the principles that I have been using and some of the examples, demos, etc. on this blog that I'll be sharing with you after the lecture. So there are two things, debugging and profiling. I'll be coming back to profiling. Now, debugging without tools, you can read a little more in detail about how I do it. But debugging without tools basically means putting print statements. But putting print statements can be done stupidly or efficiently. Stupidly would be if you realize that somewhere there's a possibility of an error and you keep putting print statements, and when you see that print statement is passed and then it crashes, then you keep lowering it down. That's just linearly scanning it. Here you need to apply some of your sorting learning, sorting understanding. The way I do it is like a pincer move. If there's a huge block of code which is buggy, which is crashing or giving a wrong output, I put a print statement at the beginning and at the end. where the print statement at the beginning is consistent and correct, at the end is something wrong. And then I keep moving it quickly inwards until I've identified the very lines of code which are causing the error. This, when implemented across like a whole number of C++ files which form a project, you can cut down on the number of files and code you're looking very quickly, and you can identify what the problem is and move ahead. A note about debugging without tools, because I'll be moving on to the actual tools used, is this is more primitive compared to without tools, but also it can be faster, because running the debugger with like very big, complicated software itself will take some of the will be memory intensive, so that it can load the whole thing and display to you the entire code stack. And it can also alter the implementation if your program is time sensitive and has threading. So in that cases, you have to resort to printing to a log file and then examining the log. So that's your only way of debugging without tools. We have about another 20. Okay, I'll go a little quickly on the hands-on. So for your benefit, I have already done a screen recording of the hands-on via my terminal and via VS Code, because not all of you will have the Linux terminal or be comfortable with it. It's a pain, actually. So I'll be going through it quickly. Even if you don't follow, you can come back to this later and try to like replicate it, so that you at least have another tool in your belt if you have to debug something complicated or more frustrating in the future. So for the demo, I have taken a subset of the files that you have been given, the default files, with just one map. So to verify that it's the same thing that you have been given, let me move this away. So I have these files, then I will compile them. I have the executable, and I will run it on the map. And then I have the robot trajectory. So it's the same thing that you have been given. But now, if I were to examine the variables as it's moving, what do I do then? So this is the first method is by the terminal. Yeah, the first method is via the terminal. The first thing I do is add a -g file to the compilation, which adds additional debugging information when I'm examining it. So the a.out, the executable over here, will be slightly larger than the otherwise like executable. And what this allows me to do is to run JDB. JDB is one of the debuggers which runs on Linux. Mac has another variant called LLVM. So those distinctions, if like, it's troubling you, then I can look into it and I can help you out. So if I run this, what I am given is a very cryptic page. If I press enter, then I can see the code. So because I put the -g file, I'm able to see this code. Now, what I'm going to do is put a few breakpoints in variables that I'm interested in. Let's say I'm interested in trajectory, in how it's reading the trajectory. There's something wrong about it, and I'm going to examine it. So I'll add a few breakpoints when trajectory is initialized, and when trajectory is done being loaded. So on this line. So I put a breakpoint on these two lines, and you can see over here that these two lines have a breakpoint in them. And let's say a breakpoint at the end, 200. So I will start the execution to show you the file name undergrad start with the argument undergrad map 10. It starts at the beginning of the function, and then I say continue until the breakpoint. So it starts over here. Now, once I'm over here, I can, I'll go a little quickly on this. I can print out things that I'm interested in. Size is absurd because it has not been initialized. If I step through one line of code and I print the size again, print trajectory.size, this makes sense. If I go through a few lines of code until it pushes a trajectory point, it has updated. And if I continue until the breakpoint on line 88 and I check it again, it has updated. Now, based on this information, you can do more things if it is different from what you were expecting. So before you run it, you'll have some hypothesis. That's also a step in debugging. You have some hypothesis of what's going to happen. And because you have localized it so much with the help of the debugger, it's easier to have these hypotheses. And then you run it and verify if the outcome matches what you were expecting. So now that this has happened, it seems like you can only put breakpoints inside this file. Now, via the terminal, putting breakpoint in the other file that is a dependency is a bit of a pain. So let's say in the planner.cpp, I want to examine the this variable. So what I'm going to do is add a breakpoint in planner.cpp and line 63. So it's going to keep executing until the plan is executed over here, and it should stop over here. So if I continue, I see that it has entered the planner and has stopped over here. I can see the arguments that were passed to it, print the variables, and step through it, and I can verify what is happening. Now, the problem over here is if I keep continuing it, because the number of times that the planner runs, this will just keep going for maybe 166 times. So what I'm going to do is I'm going to clear the breakpoint. So just deleted the breakpoint. I'm going to continue. So this will go to the last breakpoint inside this file. And there are two ways this could have broken out. It could have broken because it's caught, or it could have broken because you ran out of time. So how do you verify that? We can just print the caught variable. It's true, and so we're good. And so we completed it, and we can exit the program. So this way you were able to look into the minute lines and verify if the behavior is making sense to you. It's a lot easier than thinking about the whole program and the ins and outs of it. Now, I'll confess that this was more complicated than it needs to be. So what we're going to do is do the same thing using VS Code. And so I will delete these two files that were generated. So it's in the same state that we were at on square 0. And I'm going to show you the steps how you can set up debugging using VS Code. Referring to this, yep. Yeah, just follow the step over here. So I'm going to create a VS Code folder and two files inside it. It's going to be tasks.json, put the code inside it. But the tasks.json has a label which we'll be using in the other, and an output file which we'll be using in the other file, launch.json file. And this should resemble what you already run, what we already just ran with the executable files that we generated. The other file is launch.json. So this is the configuration that we'll be running, and it will figure out how to put everything together. Now, there's a note over here to add arguments needed with the program. Let's run it without the arguments and see what kind of error, if the error makes sense. So following what it says, we go to the file containing the main function, and then click on run and debug. There is the same label that we saw, GDB launch, that we just named over here. Inside this function containing the int main, we will run the debugger. Let's not put any breakpoints for now. Yep, verify there are no breakpoints, and then I run it, and it will fail. Why did it fail? Because the run test takes exactly one command line argument in our file. So what we do is in loss or JSON, just like we did inside GDB, we ran start undergrad slash map.mapin.txt. We're going to do the same over here. We're going to give the argument, which is a comma separated strings, undergrad is the folder name from the current folder, map10.txt. And I'm going to go back to the file containing the main function and run it again, and it should execute without any problems. It generated the output, the trajectory, etc., etc. Now, let's look at the good parts. If I want to debug the same things, I just put a breakpoint over here, inside the planner, over here. And let's try it again. So I'm just going to do Control-Shift-D, start debugger. It printed out the statement still here, and I go to the debug console, and I am stopped over here. So once I'm over here, I can check similar things that I had done in the past. Trajectory size doesn't make sense because it's not initialized. I step through one line. So stepping is via this GUI over here, which is annoying. So I step through one line. Now I check for trajectory size again, which is 0. Then I can continue using this. And then I can check the trajectory size again, the same that we saw at the terminal. Then we continue through this. We go inside the planner function. It's much easier to deal with. And then we look at these variables. Old distance to target, it's something else. Distance to target is something else. We step through once, and we see that the old distance is updated. And let's say you also want to verify, validate some of the variables if this changes somewhere along the line. So you print dx, you expand it, and there are all these things that you can do more easily inside VS Code. And then you think you can continue, you're stuck over here, like each time you run the planner, so you can get rid of the breakpoint. You can run it till the end, and it would have completed. So that's on everything for the debugger. You can go through this example again, and try it out yourself using the guidelines given here. Now, besides this, what I wanted to cover is profiling. Now, we're out of time for profiling, but I'll give you some idea of what it entails so that you can at least go away with the principle, and then you can read further on the blog. Profiling can have multiple meanings. The one that is most typically used is CPU profiling. We care about the time that your code is taking, the bottlenecks in your code, which line of code is taking the most amount of time and is kind of throttling your speed. You have to identify that line, and to do that, there are two things, like you can go without tools or with tools. Without tools is again adding time print statements. So this is again, that will be on my blog. Chrono, you include the chrono package and measure the time taken from the start of the function till the end of the function, what you want to examine, and the duration. If the duration makes sense, then you look at something else. But again, over here, you can do that sort of pincer to identify what is the bottleneck for your code. This is using the without tools, and this is what I typically use. And then there are with tools, which have Valgrind, GDB, etc. So it kind of it runs your code multiple times, and it does some sort of sampling. So I wouldn't advise you to explore it right now, but just so that you know the concept. Some of them are implemented as sampling. So they stop the program at random time, like we did with breakpoints, but random breakpoints, and see where the program, what line of code the program is stuck in. So you would have done it yourself. When you do Control C, it shows you what line of code it is stuck at. So the program does it itself, and this way, by just sampling and in what line of code it's stopping the most amount of time, it detects that this function is messed up. It's taking a lot of time. So that's another method via tools. But for implementation, for my implementation during my homework, I would do it via this profiling via measuring the time difference. How much time do you have?
Depends on the questions, basically.
So I can give you an example of two algorithms of optimizing the implementation. So it'll also be on the blog. So yeah, you have two options: Q&A, like further discussion based on what you want to know, or I can show you the demo. What's your preference? Demo? Okay, cool. So this is the question. Lead code. You're climbing a staircase. It takes n steps to reach the top. Each time you can either climb one or two steps. Give the number of distinct ways you can climb to the top. So you can implement it via recursion. I was going to implement it with like live, but I'm just going to copy it. So if you implement it via recursion, you can print the number of ways. This is just how I set up the problem. And there's some crazy requirement that the same function is going to be queried many number of times. So you run the algorithm for the required number of queries. And what you see is the wall clock time over here, 364 milliseconds. Now it ran over here, but when you put the solution in lead code, it will time out on the 45th test case. It won't work. Now, if this is part of a bigger function where you thought recursion is sweet, it's easy, and you implemented it, you realize that this is a problem. Once you've identified the bottleneck, what do you do next? That's a demo that I'm giving right now. Over here, you apply principles about algorithms, what is more efficient, what sort of like number counting is more efficient. And over here, based on practice, you would know that dynamic programming would be more efficient. So you replace this implementation with a dynamic programming implementation, and you run the same function, can get the same outputs using DP. Your time went down by an order of magnitude of 2. That's a huge difference. And this is a third problem with only 20 stairs. The problems you'll face outside are going to be huge. As they scale, your time difference, the order of magnitude will scale accordingly. So this is what I want you to take away. And when you're going and solving problems, I want you to build your own principles of how you deal with things. And if the principles are not working, then improve the principles so that you can deal with problems no matter what form they are in the future. I think that will be all. We're open for questions now.
Anything, homework, course material. Yes.
One kind of question for the homework, I mean, different people have different computers, so they want to run. And also, like, it's the